Isaac Newton gave us 3 laws. He discovered them. And we're going to go through all 3 of them. This is the first. It has a name. Does anybody know the name? Oh, do you like my joke, by the way?
Fig Mars?
Fig Newtons. Do you guys know about fig Newtons? Or is that too old? When I was your age, I always had a fig Newton in my lunch.
And then it's inertia, right?
Very good, Ashley. Inertia. Everyone say inertia. Who can tell me what they think inertia means?
Things that are moving in one direction.
Thomas.
They're like resistance to change.
Resistance to change. Okay, yeah, okay, Ashley.
Objects will keep doing what they did like before. But objects will keep doing what they're doing.
Ah, you know my version.
If nothing stops them.
No. Take a look at this picture. What do you think happened here? By the way, these slides are all, I just posted them in the materials version of the section of the classroom, along with all the worksheets. So if you want to look with me, you can be on the slides and you can look at all the worksheets and stuff too. Sorry, someone was saying there. Was that Declan? Carry on.
The one to the left, there's change, you start sliding twice.
Good, so if you're driving a big truck on the road, and you got a big trailer behind you, the brakes are working on the truck in the front, but if the trailer brakes lock up and the trailer starts to slide, it just keeps going, right? So it ends up with bad things happening. So that's an example of inertia. As Ashley said, inertia is things tend to keep doing what they're doing. Here's a video I made quite a while ago. Okay, good morning or afternoon physics classes. We have here the egg drop. An egg, a telescope, and a little dish with a glass underneath it. We're going to try to drop the egg into the glass. Neva's going to be our volunteer. This is early in June 2015. Okay, so you know what to do, Neve? You're going to smack this side of the container. Just go. But you don't put your hand through. You just whack it so that this thing is going to move. What do you think is going to happen?
The egg's gonna pop.
Egg's gonna hit the table and crack.
Or she's gonna,
The egg's going to hit the table and crack, maybe.
she's gonna accidentally hit the egg.
Taylor, what do you think?
I think the stuff below the egg is gonna move and it's gonna go straight down.
Okay, interesting. Let's see. So hard enough to make it
Right here?
right on the edge, right here. You're just going to make it go that way. Okay, 3, 2, 1, go. Hey, you did it!
I didn't see.
It went right into the water. Okay, why did that happen?
Inertia?
Inertia, yeah. What was the egg doing in the beginning?
Not staying in place.
It was just sitting there, right? So things want to. I don't know if they want to, but things tend to keep doing what they're doing. And so when Neva hit the container out, the egg didn't go with the container. The egg stayed where it was, right? And the container flew out and the egg just falls down. Okay. 1665. Isaac Newton wrote down 3 laws of things that he had observed in nature. As far as we know, these 3 laws work everywhere. We haven't seen anything to go against these yet. Newton's first law, an object's motion will stay the same unless an outside force is applied to it. And this is referred to as the law of inertia, so we call it inertia. Imagine you are driving a go-kart. Turn to your partner, or think to yourself, and try to come up with 3 situations, 3 times when you're driving the go-kart when you experience inertia. Go.
Take 30 seconds.
Braking. Yeah, when you turn, accelerating. Yep. Accelerating.
How many people have more than one? Good. Who can't think of any? Who doesn't know what I'm talking about? What's it? Who's not going to put their hand up because they're too tired? Always fun. That's good. Come and think. Okay. Give me one Jimmy. When you're turning, very good. The turning is the most interesting one, right? So if I turn the wheel, if we're all in a car and I turn the wheel this way, what happens to us? We lean, right? But is that really what's happening?
No.
Ashley, what's really happening?
What's really happening is the car is turning, but you're still going straight forwards.
Okay, good.
And so, like, yeah, so you get pushed to the side. You feel like you're getting pushed to the side relative to the car, but you're actually still going, like, straight forwards.
Exactly. So you're traveling in the car at a constant speed, and because of inertia, you would tend to keep going straight at that speed. When the car turns, you feel like you're being pushed over, but that's actually not what's happening. Really, the difference is this: you're being pulled this way. And so you end up in this position, but you're actually not moving this way. If you were to look at the car from the top, you would see the car move and your body would get pulled like this, right? And that's because of inertia. Okay, another one, Max.
Braking.
Good, braking. Yazzie, what happens when you brake in the car?
You keep going forward, but the car stopping.
Yeah, that's exactly right, yeah. You know how you feel, you hit the brakes and then you go like this? That's it. Are you really leaning over? Like, are you being pushed forward? What's happening, Adam?
The car is slowing down, but relative to the car, you're still moving forward. You're trying to get that.
Exactly, yeah. You're moving at a constant velocity, so you would tend to carry on that constant velocity. When you push the brakes in a car, are you accelerating?
Yes.
Yeah. Matthew, say that again. Negatively, very good. Amir, what does negative acceleration mean?
Slowing down.
Yeah, that's exactly what it means, yeah. So if I'm traveling this way, and I put the brakes on, I feel myself, which direction am I accelerating? Matthew's pointing this way, and he's right. So I'm traveling forwards, accelerating backwards, and so because my speed is changing in the backwards direction, I'm kind of being pulled back, right? And I end up leaning forward. Good. Last one. Who's got the last one? Ashley.
Accelerating really fast.
Good. What happens when you hit the gas?
Spin. You're back.
Boom. Back, right? We've all experienced this. Anybody have a Tesla? Here? It's good. It's good, right? If you put the pedal on a Tesla, you're like, because the torque is there right from the beginning. Electric cars have really good acceleration. So you'll notice something similar to all three of those situations. What's similar to all three of those, Ashley?
As the car is moving a certain way, you are staying in the direction that you were originally at until like the car catches up with you, or until you catch
Okay,
up
so
with the
you
car.
said, I like the way you said that. You said the car's moving the car moves in a certain way. Now, think about this. This is the real crux of all of this Newton's law stuff. If you understand what I'm about to say, you will understand all of Newton's laws. There's a difference between movement and change in movement. Okay, think about that. There's a difference between moving and change in moving. A force causes a change in motion. A force does not cause motion. When you ask 100 people on a street, what does a force cause? 99 of them will say a force causes motion, causes movement. That's wrong. That's not right. What do we call a change in motion? You just learned all about it. Taylor?
Acceleration.
Very good. Golf clap, Taylor. Nice. Acceleration is a change in motion. What do we call just motion? Yeah, velocity is just motion. Now, we don't understand that very well because if you slide a book on a table, what happens to it?
It stops.
It's going to stop, right? Why?
Friction.
Friction. But that's a force. That's a force. And it's a force that is applied to every motion that you have ever been around or seen. So you're really used to it. So you think, well, to get this thing to move, I have to push it, right? And even to make it move at a constant velocity, I have to push constantly because the friction force and my force become equal. And so it's pretty understandable that most people think force causes motion because you gotta apply a force to move something. But that's only here in this thin band of atmosphere around our planet, right? Give me an example of something moving at a constant velocity with no force being applied. Adam.
The International Space Station?
Ah, good one. Connor, what were you gonna say?
Space Station.
Really? Oh, you guys are linked up. Mind melt. Yeah, the space station is a great example. So it's in orbit, right? So it's moving. It's not slowing down, it's not speeding up, it's just moving. Is there a force pushing that thing? It's kind of strange because there is a force acting on the space station. What is the force, Connor? Gravity. Gravity is pulling it, and it is being accelerated towards the center of the Earth. We'll get into that later if we talk about centripetal force. But this motion is, there's no force on it at all. It just keeps moving. Why doesn't it slow down?
There's
No,
no
there's nothing to stop.
Good, good. There's no air, right? So that's why force is commonly misunderstood, is because we live in this ocean, right? Did I show you the pop can thing yet? Oh, we gotta do that. Let's try to do that today. Ashley, you had another example,
I was going to say a satellite or an asteroid.
right? There's another example. You're sitting on it right now. The Earth, yeah. We don't fall into the sun because we are moving with a constant velocity, right? That we're moving, if this is the sun, and we're over here somewhere.
It's very bigger.
Yeah, it's really big and too close. But we're moving like this, right? So it's interesting because our orbit is elliptical, but let's just pretend it's circular for a while. What is our velocity right now?
A lot.
A lot, yeah, but in what direction?
Oh, that way.
Straight?
Can you have a curved instantaneous velocity?
No.
No, it's only in one direction, right? So in this picture, what direction is the Earth traveling? This way, right? That linear velocity, it's a bit confusing because the Earth goes in it's constantly being pulled toward the sun, and that's why we go around the sun. That's how an orbit works. But the linear velocity, the sideways velocity, if you will, is unchanging. We don't fall into the sun because there's nothing out in space slowing us down. We are actually getting a little bit further away all the time, but we won't talk about that. Okay. Good. Very good. Very good. Very good. Why don't things do that here again? If I slide the book, why does it stop? Friction. So that's actually force, right? We'll talk about friction more later. Okay. If there's no net force on an object, then that object will stay at a constant velocity. If I put this book right here, is it at a constant velocity?
Yes.
Yes. It's
Zero.
zero, right? Unless you're standing on the moon, in which case it's 1,700 kilometers an hour east. But it doesn't matter, because it's constant, right? What has to happen for me to change that motion? You need a force, right? I have to push it. Is there any forces acting on the book right now?
Gravity.
Yes, gravity. So,
Taking gravity.
why does the book not fall?
Because another force is pushing it over.
So there's no net force. The net force is the sum of all the forces on the object. So this book is being pulled down, but it's also being pushed up. That people don't like to hear that, right? I don't like it that something's pushing up on me all the time. But it's true. It's true. Okay. We call that force the normal force. We'll talk more about that later. So right now, what you're feeling is the normal force. You don't feel gravity. In fact, you've never felt gravity in your whole life. What you feel is the force of the earth or the chair or the floor pushing up on you. And when you step on a scale, that's what you read. You read the normal force. It stays at rest. The important thing to understand is that things that are at rest, if this monkey sits on my shoulder, he stays at rest because the forces on him are balanced. There's a downward force and an upward force. What would you say about those two forces?
They cancel each other out.
Connor? They're opposite and
They cancel each
equal.
other out.
Good, Sam. Thank you. Yeah, equal and opposite forces means zero net force. And that means constant velocity. Very good, very good. I'm trying not to get distracted today, can you tell? I'm trying to go straight through. I'm being tempted though. There's lots of places I'm being tempted. I'm gonna try to keep going. Okay, if I were to take this book and hold it up, I won't get on the table. If I hold it up and drop it, what made it fall?
Gravity.
Gravity. What's happening to it as it falls?
Accelerate.
It's accelerating. It's getting faster, right? So while the book is falling, it's in the air. I'm holding it, but just pretend it's just falling. What is acting on the book?
Air resistance.
Gravity. We'll forget about the air resistance for today. There is some, but let's negate it. If there's only gravity, what's happening to the velocity of the book? It's accelerating. It's getting faster. Right. That's because there's a net force acting on the book. There's no supportive force, there's no normal force acting against gravity, and so it speeds up. So anytime you have forces that are unbalanced, you have acceleration. Okay, here's the big thing. Take your brain. You feel your brain? Can you feel it? So it's good to be aware of your brain. Feel your brain. Try to access the part of your brain that remembers things forever. It's not easy to do, but it's there. If you can find it, it's there. Not everything I say I need you to remember forever, but this I need you to remember forever. Yasmin, can you flip the door closed for us? Ready? Are you ready to put something in there?
Yeah.
Okay. Don't put everything in there. It's too much. This you can put in there. Oh, it's not even there.
Yeah, I would.
That was it. I'll write it on the board. I think it's in the next slides. Force does not create motion. That's number one. Force does not create motion. What does force create?
Change in motion.
Very good. Very, very, very important. Force does not create motion, it makes a change in motion. Every time. That's the end of that video. I'm going to give you a worksheet on inertia, and I'm going to give you a little bit of time to work on that.